Welcome back, ELE 111. We are in section 16.6, 17.6, series parallel. This is a biggie. This is a long 9-slide circuit. I don't know how you want to take notes. If you don't take notes, you won't have anything to go off of. So I recommend that you stop the video, write things down, copy what's on there, take a picture of it, embed it in your notes, whatever you need to do, that's going to be imperative. So what we're going to do here is calculate all the currents and all the voltages. We're going to determine who dominates. ZT will tell us that. And we'll do a voltage phasor at the end just for fun, just to wrap it all up. So I want you to take a look at this circuit. It's big, and there's no way to tell who dominates. There's no need for frequency because all the values that I've given you are frequency free. In other words, I've already computed that the two capacitors are 1K and 2K, or 1K and 3K. So, step one, draw the circuit, converting it to impedance boxes, which is exactly what I did here in the green area. I converted it to green boxes, to impedance boxes, and I want you to notice the important directive, which I keep asking you to do in step 2, which is to combine from the outside. Get away from where the power supply is. The ohm meter goes there, and you start calculating resistance from the opposite side over here where the red circles are. Now, there is something that I want to do on this page before we leave it. I want us to notice what Z4 and 5 are doing. They're directly in series. I don't know what Z4 is. I don't know what Z5 is. I don't care if it's a capacitor, inductor, or resistor. They're all going to have the same series circuit formula for impedance. So I add 2K and 3K with the proper phase angles, and I come up with this number, which will be useful in the next page / next drawing. Was the same formula that we used in step 1. So here's that next page, step 3. I've redrawn the circuit. I can't overemphasize how important that is. You need to take a look at the next circuit that I drew and ask yourself, hey, what is that? What is that in the circle? Is it series or is it parallel? Take a look at it. These two resistors both touch on the bottom and they both touch on the top. These are definitely parallel. So we go off and use the parallel formula, which is right here, to calculate that. Straightforward. You're going to be doing a lot of this. Hopefully you're getting better at it. And we've done everything we can with this picture. There is no more that we can do in this slide at this moment because we're going to have to compress more impedances. Here's the next phase. It says, hey, what the heck are Z2 and Z345? What kind of relationship is it? Does it look like a snake? Yes. So it's series. It's definitely series. So we grab the series formula, and we compute the impedance of those two impedance boxes in one fell swoop. And you'll note that the circuit is shrinking. Here's our last step. Look at that. What kind of circuit is that? If you said parallel, you were correct. And we've been using product over sum to compute these things. And why would it be any difference here? Z1 and Z2345 are computed to be 721.527 at an angle of negative 15.329. Now, we've gotten to the magic spot with ZT. we can look at that answer and go, hey, who dominates this circuit? Well, this diagram helps explain it one more time. You've got inductors at 90 and capacitors at minus 90, okay? And you've got resistors at 0. And they fight. They fight. If the phase angle falls in the red region, it's all resistors. If it falls in the blue region, it's all inductors. And if it falls in the yellow region, it's all capacitors. So this magic line is at minus 45 and positive 45 degrees. You know, in this online stuff, I feel bad. It feels like I'm swamping you. But boy, I'm able to go over this stuff over and over to where I think it does, in the end, start sticking with you. So we've got total impedance, and here it is. And the only thing you can do with this circuit, it's a crappy circuit, the only thing you can do is calculate the total current using Ohm's law. It will always be this way with a series parallel circuit, and so we'll compute the total current in the circuit. Now comes the good stuff. We have to go backwards from this green circuit. We have to go backwards, and we have to bring back the impedance that we took off to get to the ZT. So by inspection, we know that this is parallel, that this is a parallel circuit, and you'll notice that the battery is directly in parallel with resistor 1. You see that? 1K at 0? Well, so we don't need to solve for resistor 1. We already know its voltage. It's 10 volts peak to peak. But what we also know is that this parallel chamber, or this group, is also parallel. What that allows us to do is compute the current through IR1, the resistor right here, as 10 milliamps at 0 degrees. Very anticlimactic there. It also shows us that Z2345, which is here, also has 10 volts. Well, that's fantastic. That allows us to calculate the current going in the red direction back and forth, and we probably want to take that back with us to the next page. So here's the next page, and that block Z2345 is really just a series circuit. And look what we got on the last page. We got that current right here calculated. This helps us. This helps us because that component marked in blue is a capacitor. And because we know the capacitor's impedance and we know its current, then we can calculate its voltage. Now slow down and look at the steps. And I'm just saying I have current. It's going into that capacitor. I can see it because I'm slowing down. I'm organized. And I'm taking a look at everything that's happening here. Okay? So the voltage of that capacitor is shown right here. We take that information and we discover that we know everything about R1 and C1 in this circuit. And we also know that the fourth resistor and whatever's in 345 is computed using this formula. So we are going to need this on the next page. This is going to give us what VR4 is inside this box up here. Okay, so blow it up and we see right here that this is R4. And we know what the voltage is. It's 7.125. Oh, sorry, 7.175 from the last page. And Z3 is a parallel combination, so it's the same voltage in both of these red circles due to the fact that it's parallel. Okay? So they both get 7.175 volts at that phase angle. And we're almost done. Isn't that special? Give me a second here to catch up. Take a look at VZ23, which is in parallel with Z45. And Z3 is just the resistor, but Z45 is a series circuit, okay? If you recall compressing it. So we're going to find the current. We're actually going after, let me rub off a little bit here. We're going after this current right now. And I'm going to lock the screen in so we don't have to deal with that. Okay, so it's a series circuit in there, and it would be very useful to compute this current that we're looking at over here as quickly as possible. So the current that flows is just calculated by Ohm's law. We already know what the voltage of that Z45 is. We actually know what the voltage is of this whole cluster here because they're in parallel, right? So there's the voltage divided by the impedance of just Z45, and this gives us the current in the green arrow that we so desperately wanted. And we move into basically the last phase. I've drawn in what we just computed was right here and right here. And you see, this is just a series circuit here in blue. And both of those components are the components that we want the voltages and currents from. So since they're in series, we use Ohm's law here to compute VR3 and VC2 directly using Ohm's law with the currents that are circled in green times the impedance, and boom. We have figured out everything in this that we need to. So if I was you and I wanted to check out exactly what's going on in this circuit, I would draw a loop around these three components and say, hey, if the capacitor, the resistor, and the if the capacitor and the resistor and the resistor 3 and the capacitors, if they form a series circuit around the loop, my 10 volts here should add up. And as you can see, I'm really, really close. And if I wanted to do something like snoop around the currents, I could check to see if my total current of C1 and R1 check out to IT, and it does. And we're done.